Yeah, so we're going to talk about events first, and then this other type of CSTR as an example problem that you'll end up working today. What do I mean by event? Event is not something like physically happening. It's not, I'm not going to list a series of social events here. Events are, within MATLAB at least, whenever a variable takes on, or if you don't like the word takes on, that could be equal or equals. Let me change that to a darker gray. Some value. Whatever that value happens to be is up to you. But there are a way to detect what these are called events. There are ways to detect these events while the differential equation system is solving. So that, for example, if you look on your project and it says, solve this until either the volume hits a particular size, or the temperature hits a particular value, or the conversion hits a particular value, or the pressure hits a particular value, rather than just starting off with small volumes and solving the thing over and over and over again until you hit one of these criteria, you can tell MATLAB to just keep an eye out for all of these criteria at the same time while it's solving. And that's what an event is called, or that is why an event is useful. Any of those things happening individually are considered events. So, for example, the event that you might see in a project would be perhaps you're going to plot volume and temperature of your reactor, something like this. And if you're going to do the adiabatic case, which I think comes up on all of your projects, as you start to solve this thing in the adiabatic case, you'll notice long before you get to the total volume way out here, which I think in some of your projects is something like 150 cubic meters or something like that, the temperature will start to explode. It doesn't quite asymptote, like vertically, but it starts to go off really, really high, like into the thousands of Kelvin very, very quickly. The ODE45 solver will continue to solve that problem regardless of how high the temperature is until you get to like millions of Kelvin or something. It's just going to keep going until it hits 150. The problem is that's not really particularly physical, and it can be very hard to interpret that solution when it comes out as actually being correct or something. And so what you can tell MATLAB to do is look for an event, establish a maximum temperature, something like this, and say, ODE45, as you are solving, keep an eye on your temperature. If your temperature ever equals that Tmax, or in that case really exceeds Tmax, stop integrating. Just stop the whole solution right there because you've gone as far as we need to for all reasonable purposes. And it will cut off that remaining portion here. It'll stop this volume maybe at something like 20. And even though you told it to solve out to 150, it says, I don't need to get all the way to 150. Long before I get to 150 on volume, I hit this event that you have indicated of Tmax, and that told me to stop. And that, if you couple several of these events together, is a convenient way to solve a lot of those project problems because they have differing stopping conditions. If you don't know what I mean by differing stopping conditions, that probably means you haven't looked at the problem statements at all. Take a look at the problem statements. As I had mentioned earlier in the class, the reason that you stop integrating in a couple of the problems is not because you necessarily get to the maximum volume of the reactor, but the pressure hits some value, or the temperature hits some value, or the conversion hits some value, something like that. That said, events, just like the F0 function, are not required for the project. If you're not comfortable using events, you don't have to use events. You can get around all of this by just changing the V parameter. So you always set a V span in your differential to decide how long to integrate. If you just keep messing around with that V span, you will eventually get to the same place. This is just a little bit more of a convenient way to stop it whenever you need to. And you no longer have to look at multiple variables when you get those output values. You can rely on the events to detect whatever it is you're trying to stop for. The general syntax for an event function looks somewhat similar to our ODE function. So you start off with the word function, like we're used to, And then your event function always has three outputs. One of them is a value. One of them is a flag that's called isTerm. You can name these whatever you want. I'm just shorthanding them to this. And another one is dir. We're going to explain each one of those. And then those are equal to something, whatever function name you want. And the inputs are the same inputs that you would have to ODE 4.5. So these two values sorry, not ODE 4.5. Whatever your ODE function is, you have access to all those same variables inside your event function. The other values over here on the left, so any of the values that you have, these correspond to events to look for. So those would be things like look for times when temperature is 1400, look for times when, I don't know, weight is 100 or conversion is 60% or whatever those events are that you're looking for. Those are going to be what we refer to as values. And we're going to get an actual example of what a value is. The isTerm is an easy one. It's always going to be equal to the number 1. The reason it's equal to the number 1 is because whenever one of these events occurs, we want to stop integrating. We have no interest in continuing that integration after we hit one of these events. We just want to stop. If you were to put this as a 0, then it would say just flag it as an event occurring, but don't actually change anything. Which there's usefulness for that as well, but not that we're interested in. Similarly, direction is an easy one. It's always going to be equal to the number 0 or potentially the vector 0. And what the direction means is stop on either the value as it's rising or as it's falling. So that can give you a little bit of flexibility. For example, if you would like to allow your reactor to exceed 1400 on the way up, but then not fall back down below 1400 on the way back down. You could use this direction thing to say, let it go ahead and go up over 1400, but never come back down below 1400. Our stuff doesn't really matter, right? As soon as you hit that particular threshold, stop integrating. So everything that we're going to do, regardless of how you get to that particular event, whether it's on the rise or on the fall, we want to stop integrating. So our dir or our direction term is always going to be equal to 0. And that's about it. The rest of the function syntax is mostly coming up with how do we detect this value? How do we calculate it? The way that we go about calculating those values comes out the same way that we calculate anything else in our ODE function. That's why the inputs, the W and the Y over there, or the V and the Y if that's what you're integrating over is something like a V. You have access to all the same variables that are being calculated as you're actually solving the problem, so you can flag any of those as values. You may have to recalculate some of the intermediate values, but some of them are also available. So I'm going to stop. That's actually as far as I need to go here. I'm going to show you an example of how to use an event on a problem that we've already solved, and then I will post that on TritonEd along with this short little like 8-minute lecture that I just gave there, so that you can practice it if you want to use it on a project.